Next, I am going to also introduce a very important concept known as the concept of conjugate points. It turns out that the moment the solution to this Jacobi accessory equation contains conjugate points, we will neither get a minima or a maxima. So, the extrema that we get will neither be a minima or a maxima if we are to find some conjugate points, and later on we will see that the non-existence of these conjugate points will give us the necessary as well as the sufficient condition for the existence of minima, right, and the same result holds for maxima with the integrand taken with a minus sign. Okay. So, let us see what are these conjugate points. So, let us say, so conjugate points are the solution to the Jacobi, are the roots of the solution to the Jacobi accessory equation, such that they are the roots of the same solution to the Jacobi accessory equation, such that these points are not equal to each other, so these points are not equal to each other. So, what I said is the following: let x naught be a real valued point, and let kappa in R minus x naught, right, is another point, right. So, if there exists a non-trivial solution, there exists a non-trivial solution to my equation 7 satisfying u of x 0 is equal to u of x 1 is equal to 0, then I see that kappa is a point which is conjugate to x naught, point conjugate to x naught. So, that is the definition. First of all, this new point kappa should not be identically equal to x naught, and they must both be the roots of the same solution to the Jacobi accessory equation. Okay. So, what is so special about these conjugate points? I am going to highlight the importance of these conjugate points step by step, starting from some small results, let us say in the form of a lemma. So, my first lemma, let me term it as lemma 5, we have described up to lemma 4. So, so I have a lemma 4, right. Let me go back. Yeah. So, I have discussed already lemma 4. So, suppose I have my f which satisfies the condition of lemma 4. What is the condition of lemma 4? That f is smooth and satisfies the strengthened Legendre conditions. So, let f satisfy conditions of my previous lemma 4, which is mainly that f is smooth, it is continuously differentiable, and the strengthened Legendre condition holds. The strengthened Legendre condition holds, right. So, if these conditions are true, and suppose there are no conjugate points, we do not find conjugate points to x naught in this half open interval x naught to x 1, we do not find a point conjugate to x naught, then there is a non-trivial solution to the Jacobi accessory equation, right. So, I am stating this lemma without proof. So, then there exists a non-trivial solution, u to 7 such that u is not 0 for all x in x naught to x 1, right. So, if we do not find conjugate points, it is guaranteed that there is a non-trivial solution to the Jacobi accessory equation. Okay. So, then so I can summarize my results in lemma 5 and lemma 4. So, again recall lemma 4 is that suppose Legendre condition holds, then the secondary variation is positive definite, right. And then suppose in lemma 5 says that suppose Legendre condition holds, then there is a non-trivial solution to the Jacobi accessory equation, or in other words we can find the link between the non-trivial solution to the Jacobi accessory equation and the second variation being positive definite, which is going to give the sufficient condition between the occurrence of conjugate points leading to the positive definiteness of the second variation. So let me state the result. So what I said is lemma 4 previously discussed and lemma 5 can be combined to give me the following result. I am going to write this combined result in the form of a theorem 25, which says that let f be a smooth function of its arguments x, y, y prime, and let y be an extremal, let y be a smooth extremal, for the functional, let y be a smooth extremal for the functional j such that f of y prime is greater than 0, such that the strengthened Legendre condition is positive for all x in x0 to x1. Then if there are no conjugate points to x0, then I am guaranteed that the second variation of the functional is positive definite. So if there are no points in the half open interval x0 to x1 conjugate to point x0, then I am guaranteed that the sufficient condition I am guaranteed that the second variation is positive definite. The second variation, that is my del square j, is positive definite, right. So this is just a combined result of the two lemmas we have just discussed. Okay. So as I said, this result provides us with the sufficient condition or the link between the non-existence of conjugate points and the positive definiteness of the second variation. However, we still have to find the necessary condition, that is the other way round, linking the positive definiteness to the non-existence of the conjugate points, and also further we have to find the link between, or the if and only if condition between the second variation being positive definite and y the extremal being minimum, right. So as I just said, this theorem is the sufficient condition, provides us with the sufficient condition, or it is the link between the absence of the conjugate points, and positive definiteness of the functional, definiteness of j, right. So that is what it is. Okay. So then so let me highlight this result with a small example. So the example that I have is as follows. So let my functional j of y be integral from x0 to x1 y prime square dx. So my Jacobi accessory equation in this case will be, recall that my accessory equation is as follows. So it is del x of f y prime u prime minus b times u is equal to 0, and I see that where so in this case my b will be 0. students can check this, and my f y prime will be 2, right. So, from here I see that the equation reduces to the following, or the solution u of x is alpha plus beta x, or a straight line, right. And from here I can see that only the trivial solution will satisfy the existence, the non-trivial existence of conjugate points. Okay. So, from here I can see that only trivial solution can satisfy conjugate point condition. Only trivial solution can satisfy conjugate point condition given by u of x naught is equal to u of kappa is equal to 0 for kappa not equal to x naught, right. So, this is only possible that when u is identically equal to 0, but by our theorem we cannot accept a trivial solution, right. Or in other words, we can also see that this particular second derivative is positive. So, in this functional the strengthened Legendre condition is also satisfied. The integrand of the functional is smooth function of y prime, and also the Jacobi accessory equation tells us that there are no conjugate points. The conclusion is that the second variation is positive definite. So, no conjugate points, no conjugate points to x naught in the open interval x naught to x1 implies that the second variation is positive. Okay. Okay. So, that is how we are going to use our result described by theorem number 25. So, as I just said that the result that we have described in that previous theorem is all about the sufficient condition linking the non-existence of conjugate points to the second variation being positive definiteness. How about the necessary condition? So, we now have to show that the absence of conjugate points is also a necessary condition for the positive definiteness of the second variation. So, we will next we show that absence of conjugate points is also a necessary condition for positive definiteness, right. So, the absence of conjugate points is going to serve as the necessary conditions as well. So, I am going to right away describe this result in the form of a theorem, but before that in the form of in fact two theorems. So, the first theorem gives us the link between the positive definiteness of the second variation and the absence of the conjugate points. So, I denote this theorem as theorem 26. So, this is going to provide us with the link between the positive definiteness of the second variation and the absence of conjugate points. Okay. So, the result is as follows. So, suppose my integrand f is a smooth function. So, let f be a smooth function, right, of its arguments, and let y be an extremal, be a smooth extremal. So, we always assume that y satisfies the Euler-Lagrange equations for the functional j, for the functional j which is integral of f dx from x naught to x 1, such that the strengthened Legendre condition holds for all x in x naught to x 1, then I have the following two results. The first result says that the second variation is positive for all eta non-zero, right. So, then there is, if this holds, the second variation is positive definite, then there are no points conjugate to the point x naught in the entire closed interval x naught to x 1. So, this means so then there are no points conjugate to x naught in the closed interval x naught to x 1, and the second result says that if this second variation of eta comma y is non-negative for non-zero epsilon, then again the same statement holds to the point x naught in the open interval from x naught to x 1, right. Well, the first one is half open interval. Okay. So, what is this result? This result gives us the necessary condition or the link between the positive definiteness of the second variation to the non-existence of the conjugate points, right. But now we need another result which links or provides us the necessary condition as well as the link between y being the minimum, the extremal being the minimum, to the second variation being positive definite, and that will complete the cycle. So, the result that we have is now the result that I am going to write again in the form of a theorem will be the combination of this particular theorem, that is theorem 26, and a previous theorem that we had described in my last lecture, namely the link between the positive definiteness of the second variation and y being the local minima. That was theorem 23. Okay. So, theorem 23, this was done in our previous lecture 16, and this theorem above, theorem 26, gives us the following result. It tells us that suppose it gives us the following result, which is now the necessary condition we are after, or also a more refined necessary condition known as the Jacobi necessary condition, right. So, this is a more refined necessary condition by Jacobi, refined necessary condition by Jacobi. It tells us that theorem, I denote it by next theorem, theorem 27, let y be a smooth extremal, let y be a smooth extremal for the functional j of y given by integral from x 0 to x 1 f of x y y prime dx, such that for all x in x 0 to x 1 f of y prime is positive. So, we are assuming the conditions of smoothness as well as the Legendre strengthened Legendre condition for the extremal y, right. So, this is greater than 0 along our extremal y, and if y produces a local minima for j, then there are no conjugate points in the open interval x 0 to x 1. If y produces a local minima for our functional j, then this implies there exists no points conjugate to x naught in the open interval x naught to x1, right. So, the necessary condition for a minimum is the non-existence of conjugate points, also known as the Jacobi, the necessary conditions by Jacobi. So, the non-existence of conjugate points is a necessary and sufficient condition for positive, certainly positive definiteness of the second variation. But how about, is it a necessary condition? Is it? Well, we have certainly shown that the non-existence is a sufficient necessary condition for the existence of minima, but how about the non-existence of conjugate points being a sufficient condition for minima? To finally state that result, we have to define what norm we are talking about. So, what is our function norm, right? So, what I have is, let us first quickly describe the norm in which we are working, or the norm with which we are describing the distance between two functions, right. So, we are now going to look at so right now, in earlier this is the necessary condition, right. So, this is a necessary condition. So, to look at sufficient condition, we now look at the norm of the function space. We have to define the norm, right. So, the sufficiency is not clear right now. So, it is not clear because we have not described the function norm, right. So, let us define the function norm. Let me define the one norm on our space. So, on the space which is C2 of x naught x1. So, C2 of x naught x1 is the second order continuously differentiable functions. By the following, I define my one norm of y to be the supremum of mod of y for all x from x naught to x1, plus the supremum of mod of y prime for all x from x naught to x1, right. So, this is how I define my one norm, and with this one norm I can describe the definition of the so called weak minima as well as later on a strong minima. So, I am going to talk about the concept of weak minima. So, suppose j from this function space to R has a, so this functional has a weak minima, it has a weak minima or weak local minima, has a weak local minima at y in the set S. Y is an extremal. So, without saying much, we are always assuming that we are working with extremal solutions. So, suppose y is an extremal, if there exists a positive number delta, right, delta which is positive, such that the difference of the perturbation of the functional or the perturbation of the functional or the difference of the functional is greater than equal to 0 for all perturbed extremals in S, such that the difference in the extremal and its perturbation is bounded above by delta, right. So, if that is true, then I say that J has a weak local minima, right. So, similarly I can say that J has a weak local maxima, right, if and only if minus J has weak local minima. So, I do not bother about local maxima at all, because the minus of the local minimum, the results with a minus sign will give me the results for the local maximum. Okay. And then further let me also describe, so this is, let me call this as 1. So, I also describe another norm, the the 0 norm as follows. So, I define my 0 norm on C2 of x 0 x 1 by the 0 norm of y is the supremum of y for all x in x 0 to x 1. So, this is the supremum, right. Okay. So, certainly if the function is bounded above by the 1 norm, it will be certainly bounded above by the 0 norm, right. So, with the 0 norm I can define another concept of the so called strong maxima or strong minima, right. So, this is my definition of weak minima. So, I can define my concept of strong minima or even strong maxima similar to the weak minima or the weak maxima case with my 1 norm replaced by 0 norm, right. So, in the same definition as in the previous slide, if we replace our 1 norm with the 0 norm, I am going to get the result for the existence of a strong local minima or local maxima, right. Okay. So, certainly if within the definition, if the function satisfies the weakness condition, then it will certainly satisfy the strong condition. So, in our definition, in our previous 2 definitions, right, certainly if I have that, if the perturbation of y satisfies the weakness criteria, then it must satisfy the strong criteria, right, strong criteria, or in other words, well, this is a strict inequality, right. So, this is what we have, this is a strict inequality here, so strict inequality. Okay. So, the implication is certainly if an extremal is weak minima, then it is bound to be a strong minima, and the same result holds for maxima. So, weak minima implies strong minima, but the vice versa does not hold, right. It is clear to see why. Okay. So, we are ready to give our important result of the sufficiency of the local minima, and the result is as follows. So, I am going to state, once we have described these norms, I am going to state the result. Theorem 28, namely the sufficiency conditions, which is the link between no conjugate points, and weak minima, and that will complete our picture of if and only if criteria for non-existence of conjugate points linking to the existence of y being the extremal being a local minimum, right. So, the result is as follows. Let my y in the set S be an extremal, right, for our functional j, which is given by integral of f dx, which is a fixed point functional, and suppose that this extremal satisfies the strengthened Legendre condition. So, suppose that along this extremal, the strengthened Legendre condition holds. Along this extremal, the strengthened Legendre condition holds, or I have that y prime at f of x comma y prime is greater than 0, is satisfied for all x from x naught to x 1, right. Then the sufficiency condition says that suppose further, if there are no conjugate points, then we are bound to get a weak local minima. So, suppose further there are no points conjugate, suppose there are no points conjugate to x naught in x naught x 1, then J has a weak local minimum. J has a weak local minimum at my extremal y. Okay. So, that is the result which completes our discussion or the link between the non-existence of conjugate point and the existence of local minimum.